Hey everyone, this is Matt with Learn Everything About Design, and in today's video we are going to be looking at doing a flow simulation of airflow for our duct that we created in our series. So I had a couple of comments asking for me to elaborate and talk about flow simulation and how the performance of the ducts are and things like that. So this is a huge topic, and I am by no means an expert in simulation. I do plenty of simulations and I know my way around, but just keep in mind that there is, garbage in, garbage out when you're talking about simulation. So if you don't have good inputs in terms of the settings, then what you get out is going to be garbage. With all that said, also note that I tried out and learned a new piece of software for this video. So I don't have a ton of time in SimFlow as I just started using it, a day or two ago. But I think I have enough down that I can walk you through the process of doing both internal and external flow. SimFlow is free. There is a paid version. The free version does, of course, have limitations, which we'll talk about. And mainly they're going to be in limitations in things like the number of CPUs that you can use for calculations, the number of nodes that you can have. But the first thing that we need to know is what inputs we need. What geometry do we need to bring in? SimFlow is unique in the fact that it does actually allow you to bring in mesh bodies. I went ahead and created a surface for the bezel, for the bumper, and the air dam, and I created small sections because, again, there's a limitation for the number of nodes we can have. The way I did this, I actually went to Blender, and a model of the Starion that I created a couple years ago, or at least I started probably in 2020. I don't really know when I started it, but anyways, this is based off of pictures, and it's close enough for what we need to do. So essentially what I did was I took the bumper and the air dam and I exported them as their low polygon count quad mesh, and I converted those to T-spline freeform bodies in Fusion. So it's a pretty simple process. You just export an OBJ so it can be a quad mesh. And then in a freeform body, you go to Utilities, Convert, and you can convert a quad mesh to a T-spline. Now, it's not direct because depending on how the model was created in Blender, I had edge weighting and things like that doesn't translate, but it was close enough for me to be able to create these bodies as surfaces that I can use for simulation. For the bezel, I just took the mesh into Quick Surface and did an auto freeform and wrapped it. It wasn't completely closed, so it is still a surface. But again, it's not really critical for what we're doing here. It was just something that that I had. The next thing to know is that this is great for external flow. If we want to see what happens when wind hits the bumper and gets sort of into this duct area. But when we want to analyze the flow inside of it, then we need to create a solid body for the inside. And the way that I went about this process is first in the solid tools, I just went in and we had this opening here for, essentially for that little tab. I just selected and hit delete to patch it. And then in our surface tools, go to offset, chain selection, and select the inside. And then we can essentially patch it here. We'll do the same thing on the back, patch it here, and then stitch those three together, and that'll give me a solid body for the inside. So I've got this piece here that can be exported. So again, with SimFlow, you can have a mesh body, but in this case, I would just go to File, Export, and save everything as step files. So that's what we're going to do. I will put a download link in the description of the video. You can go ahead and continue on. Obviously, I included it in the duct series, but I added this tube on the back just for this video, and I'll include this solid body, or at least include the file before the solid body is created, and then you can create your own and play with it. Once we get into SimFlow, to get started, we'll look at external flow first, and then we'll go to internal flow. But what we're going to do is create a new case, and I'm going to call this external bumper flow. We'll create that. And when we get started, our first step is to bring in geometry. So we'll click on this Add New. I need to go to where I have it saved. and I'm going to be bringing in this CFD export. So essentially this export is going to include 3 surfaces, which is the air dam, the bumper, and the bezel. And it'll also include 2 solids. You can see here 2 solids, which are going to be the 2 intake ducts. I don't want to make them a single body, so I'll click no. And as I rotate this around, you can see there's 2 different icons. So these 2 mean they're solids, and these ones are their surfaces or shells. So I'm just going to double click on them and rename them. This one will be the air dam. This one will be the bumper. Renaming them is going to be helpful. And this one will be the bezel. This one here is going to be the brake duct. And this one will be the intake duct. So now that we have them named, the next step in the process is to mesh. So we go to this hex meshing section. We need to click this icon, which means that we want to actually include it as mesh geometry. These other icons are different types of meshes. We'll explore the boundary layer when we do our internal flow for the duct. But for right now, we just need the first one. Then we want to click on each of them and determine the refinement level. So this is where we start to run into limitations with a free version. We can't go crazy with these refinement levels because we're going to actually just run out of the number of nodes that we can use. So the bumper, the bezel, the brake duct, all are going to set to max of 1. And I'm going to set the refinement for the intake duct, the one I'm really curious about, to a max of 3. Next is the base. And this is essentially the area where the calculations are happening. So this has sort of twofold here. One, it needs to encompass our object. So I'll select auto size. I'm going to change the Y value, the second value, to be minus 0.1, which will basically extend it a little bit in front of the bumper. If you're looking at external flow, you need to be careful that your boundary isn't so tight to the object because it can influence it. If I was curious about air flowing around the side of the bumper or up, then I would probably mess with those as well. You can bump them up just slightly. So for example, this is 0.728, maybe you can make it 0.73 so that there's a tiny gap on the side. And then for Z, we'll make that 0.5, let it grow a little bit. The divisions here, these are basically going to be where the calculations are happening. So these numbers should be appropriately sized based on what you're looking for. But again, you're going to run into limitations for essentially you're going to run up against a wall for how big you can make these based on a free version. The other thing that we want to do is we want to determine these boundaries. So basically, this one here is going to be our left wall. This one here will be our right wall. This one here is going to be the inlet. This one here will be outlet. This is going to be the bottom, which we're going to set it as a wall. And this one here will be the top. So everything is going to be set as a patch with the exception of the bottom is set as a wall. Next thing is this point. This needs to lie inside of the boundary. So when we're looking at internal flow, it'll have to be inside of that duct. For external flow, we just need it to be inside of this cube. So I'm going to increase the X value. I'm going to increase the Y value just slightly, and I'll increase the Z value. So basically, I want that to be up in this boundary, but I can't have it inside something. So the Y value is probably too big. Let's make it 0.05. Actually, let's make it a little smaller, 0.01. So it's not in any of the meshes, it's just in front of them. And then we can go ahead and go through the process of meshing this. This is where, again, you're going to find limitations based on the free version. You can get a 30-day trial of the software to play around with it. Right now, again, I'm doing everything in the free version, so I'm working within the limitations of the number of processors I can use, the number of nodes that I have available. There is a slight chance that this is going to run up against that node limit. And it does take longer to calculate, especially when you start to increase those settings as they get a little bit larger. You're going to possibly get warnings that say you've exceeded the number of nodes for the free version. All right, so once it's done calculating, there are a couple things that we want to do. First, we can see that we've got bunch of different colors. So we want the air to hit those objects. We do want to change the display. So we're going to click on this mesh, and the top, the right, the outlet, the left, and the inlet, we all want to hide so we can see the bottom. And we get a good idea of what the mesh looks like. So remember with the intake duct here, we set the refinement level up to 3. And with everything else, the max refinement was 1. So you can kind of get hopefully a visual idea of what that difference looks like. So now that everything is meshed and we have all of the zones defined here, we're going to go into setup. This is going to be steady state and incompressible. And then we're going to pick the simple solver and select it. Once we do that, it's going to open up some options for us. First is turbulence. We need to set that. We could leave it at laminar, but for most external flow, they recommend in the help files to use RANs and to basically use this model system. What I would say, again, because I've only been using this for a day or two, is to go through the help file and tutorials and look at the types of studies you're trying to run and use the default settings that they set. The next thing that we really need to focus on is boundary conditions. So right now, inlet, we're going to have be a free stream. So free stream, we need to define a pressure and a velocity. So these numbers can be a little bit tricky. The velocity in the y direction, we're going to set at 28 meters per second. So essentially what we're looking at is a car driving 55, 60 miles an hour. So we're looking at essentially the velocity that's equivalent to that. On the pressure that would be built up on a bumper based on that amount of pressure approximately equals 127. So that's where these numbers are coming from. I'm not just pulling them out of the air, but that's essentially where these two numbers are coming from. Looking at driving about 55 or 60 miles an hour, what does the pressure built up on the front of a car, on the front of a bumper look like? Because this is my assumption. That's what's going to happen is this area will be pressurized, and then the flow, essentially the speed of the air, and that's how we come up with these boundary conditions. Monitors is another area that we want to focus on. We're going to do some sampling. And basically what we want to do is create a slice plane. The first slice plane I'm going to set essentially as a horizontal plane that goes through these ducts. So I need to move the Z value up until it's in the middle of the duct. So about 0.16 maybe. And then the fields, we want to look at pressure and velocity. Then we'll create another one. We're going to set the normal in X. So we'll set basically 1, 0, 0. And then in the X direction, we need to move over that 3.31. That'll kind of put it right in the middle, maybe a little bit less, maybe 305. And essentially what's happening is as it's calculating, as it's solving, it will give us a plot. So we can go to run, we can run the simulation, and during the solve, we'll get a graph talking about things like the residual pressures, but we've got the slices section, which will show us what the velocity and what the pressure is doing. Now, as it's calculating, they may go gray like this as it's recalculating the next iteration. But again, another thing to keep in mind is as we look at these, we don't have an entire car, right? We don't have the hood. We don't have the rest of the bumper or the fender. So the airflow that we see basically up around this pipe is not realistic. But what we're seeing here is we've got, currently what we're doing is we're looking at velocity. We've got the velocity of the air increasing as it goes into this pipe. And you can kind of see what's going on here. And as I look at this, I would say, well, I probably don't want to use a 90-degree bend here. Maybe something like a 60-degree bend would be able to help with the flow of air because we've got a low pressure system right here and high pressure right around those corners. And if we rotate this view to look at the top, we can see what's going on here. We've got these areas of low pressure right at the corner of the duct. So the air is hitting the bezel and it's probably doing like a little swirl here. And it's a much more direct path on this right side. And you can kind of see what's going on with the brake duct as well. Again, the brake duct was really low resolution, so I'm not going to put too much stock in that. And then we can change the plot to look at the pressure. So once again, if we look at it from the side, we've got a really high pressure zone up front and fairly consistent on the inside. You can see there are some areas around the corners. Those are low. And again, that kind of indicates maybe not using 90-degree bends there. And when we look at it from the top, you can see what's happening. We've got these pressure zones that are basically decreasing as we get inside, but nothing drastic that would indicate a potential problem. So that all happened directly inside of SimFlow. I'm going to go ahead and save this, and then I'm going to start a new case. And in the new case, what we're going to do is we're going to talk about internal flow. So internal intake flow. We'll create that, and we'll open the current window. We'll make sure that those changes are saved. And in this one, we're going to go through the same process. We will export the results and talk about some additional post-processing that we can do. But everything so far was done directly here in SimFlow. So we're going to start by, again, adding new. And of course, it doesn't remember where I was, so I have to go find the files again. I've got export v2. The export v2 is going to bring in the solid inside of that duct, but it'll also bring in the duct itself, as well as the bezel, the bumper, and everything else. And we don't need all of that. So basically, what we want to do is delete anything that we don't need. So all the shells, which are, again, surfaces, go ahead and delete those. And we're going to focus our attention just on this duct. So now that we have the duct defined, I'm going to hold down the control key and left click the front face, and we're going to create what's called a face group. So this first group here is going to be the, we're going to call this one inlet. So we're going to hit escape, rotate this around, hold down control, and select this face here, create another face group, and this one's going to be the outlet. We need to make sure that this does say one face for each of those. It is possible to create a face group with nothing selected, so make sure that it does say one face. And then we'll go into our hex meshing. For this one, we want to create what's called a boundary layer mesh, so we want to use these first two options. And the refinement, again, play around with these numbers, but refinement of 1 or 2 is probably going to be fine. Notice that it says face groups down here. We've got inlet and outlet. That's going to be important later. The base, again, we're going to do auto size. Don't really care too much about having this be larger, but one thing we do want to pay attention to is the divisions. The divisions are essentially going to be the cell sizes that calculate the results. So we do want to make sure that we play around with those. Again, on a free version, you're going to have a limitation, so you will have to be careful with how big those get. Also note down here these boundaries for like wall and floor that we did with the external flow. I'm going to leave them as is for this one because we're looking at internal flow. The point needs to be inside where the flow is. So we can use a selection option to pick a location from the 3D view. But what I'm going to do is I'm going to start by increasing the Z. Let's go up to maybe 0.14. The Y, let's try 0.15, and then rotate this around. And I know that the X is about 0.31. And I just need to make sure that that is inside of the pipe. If it's not inside the pipe, it's going to assume that we're doing external flow. So I'm going to make sure that the Z is, let's say 0.16. There we go. So now that point's inside, we can go to mesh and mesh this. Since we're only dealing with a single body, this should happen a little bit quicker. Keep in mind, again, it is looking at the entire boundary. So that box with the number of divisions, 25, 20, and 20, that's all going to come into play with the calculations. But we should see the front face yellow, the outlet here, the back face is green, and then we've got the red, which is our boundary. So as we look at this for our mesh definitions, the boundary should be a wall, but the inlet and outlet should be defined as a patch. That'll let us determine them as inlet and outlet flow a little bit later. Then we'll go to setup, steady state incompressible. We'll use a simple solver again. And this brings up some additional options. So turbulence, we're going to use the same option that we use for our external flow. We need to go into transport properties and material database to enable and apply air. And then we want to go into our boundary conditions. So again, the outside is essentially assuming it's a pipe, it's a wall. And then the inlet and outlet we're going to have to define. So the outlet we can use as outflow or pressure outlet, depending on how you want to define it. So if we do a pressure outlet, fixed value at 0, the inlet, however, we need to determine whether we want to define it as a pressure inlet, velocity inlet. What I'm going to do is I'm going to do a free stream, and I'm going to use those same values that I used for the external flow. So basically we're looking at 127 and then 25 or 28 meters per second in the y direction. So it's because x is left and right as we're looking at it, z is up and down, y is forward and back as the car would travel. So now this is telling it that on the inlet side, we've got this sort of free flow, free stream flow defined at these values, and the outlet is a pressure outlet set to 0. Next, we're going to go to monitors, and in sampling, we want to create some pressure and velocity slice planes. So these slice planes, we need to define where they are. So in Z, remember about 0.16 is where we put that point. So that's going to give us a good idea what's going along here. And then the other one we want to do, we're going to set it at 1 in X. And then it was about 0.31. That'll get us right in between. And now we can run it. So remember that when we're running it, we will have the ability to see these slices, what's going on in real time. And just like with the external flow, we can get a good idea as to what this means for us. So when we look at pressure, for example, we see high pressure at the front, which we would expect to see if this is just open to the front of the car as it's driving down the highway. And then what we're seeing here is on these 90-degree corners, we're seeing these low pressure areas and high pressure around the larger portion of the radius. And this would tell me as I'm looking at it that I should not use 90-degree bends, but instead make maybe a 60-degree sweep up if I can. Then I can also look at the velocity, and it shows the same kind of thing. We've got these areas where the velocity is inconsistent, and this is true because as we go around these corners, we tend to have air kind of sticking and creating these eddies, and that's going to affect the flow. When we look at it from the top, what we see here is kind of what we would expect to see. We've got more of a flat section coming from where the brake duct is, and on the right side, we've got more of a straight flow. So you can kind of see the difference here in velocity and this corner here. So what this would tell me is as I'm designing this in both the pressure and in the velocity, it would be much better if I could get this to transition quicker, or this, maybe make this front plate flat and then have the duct start over here. That way I wouldn't have this issue here. Now, remember when these were designed, it's because there is some sheet metal that's kind of in the way, and that's where the mounting points are. So there's only so much that you can do, but if you're trying to optimize a design like this, those are the things that I would look at. I can see that there is definitely a pressure and velocity difference at this corner, so I would try to smooth that transition out if possible. And then looking at it from the side, I would say, well, probably using 90 degrees is not the best thing that we would do. We would probably want to just get this to turn up a bit better, have a more direct path to get that air into an intake or into a compressor housing or something. From here, what we can do is post-process, click export, and then once it's done exporting, it should say end down here, we can open up Paraview. So again, still free version. what we're going to do is click Apply in the Properties, and this is going to open our duct for us. Now, as we look at it, not much is going on. We can change the color map presets, which is this button right here. It'll open it up on the right-hand side. You can pick another color bar. You can determine what you want to see. So again, velocity, and we'll pick the color bar. You can change the display to things like points. You can also change the display to show the flow lines. But really, probably what you would want to do is create a plot where you can actually show the stream tracers. So we're going to click Stream Tracer. We're going to change this to be Point Cloud. And what we need is this actual sphere here to be inside of the duct because the lines are going to be coming out of it. So using my display options, I'm going to go Z. I'm going to move this around, maybe put it right there. And then we'll go to a side view, maybe put it right there. It's probably going to be a little too big, but we'll try it. And then we're going to say apply. Now, when we apply this, it crashed. I've had this happen before. All right, so I'm going to go ahead and push the data again. Well, again, we'll hit apply to bring everything in. Go to the setting. We will change this to point cloud. Put this here. And what I'm going to do is I'm going to reduce the radius value. So right now it's 0.03. Let's make it 0.02 and try to get it inside. And then we'll apply it. So the problem that happened is with that, the radius value being larger than the tube, some of the traces were inside and some were outside, and I think that's why it crashed. We can change our color map and we can get basically a flow plot of what's going on. So this is pressure right now. We could change that to velocity, which is U, and reset the color. So we can see here that the velocity is changing, and we can tell based on the color plot that it's slowing down on the outside here. It's kind of pinching there, so it's going high there, but you can see it's going yellow to the orange here. And again, this is looking at basically pressure or velocity, but there are other settings that we can take a look at as well. But probably the two that you're most interested in are the pressure plot and the velocity plot. So once again, you can play around with all these different things. I have found that just the section plots directly in SimFlow seem to be the most instantly helpful, and the UI and UX in here is very straightforward. There are additional options that we can do in terms of calculating additional information. It'll display down here. You can also go back when you are setting up your monitors and you can create additional plots to look through here. You're not going to be able to do the traces like we did by exporting everything, but you do still have some options. You can get some good information out of this that will help you determine whether or not you want to make changes. So something to keep in mind here is that there are plenty of different pieces of software out there. Some are free, some are not free. You can do a flow generative design study in Fusion, but you'll need the simulation extension to be able to solve that or use tokens or credits. There are other ones like OpenFoam that are free. They tend to be more focused on Linux-based systems. I tried to run it on my Windows-based system, and it was just more cumbersome and complicated to get it going than SimFlow. So that's why I decided to use SimFlow for this video. I'm by no means an expert in CFD or SimFlow. I've only been using it for a day or two, but hopefully this is helpful enough to get you started, and you can play around with your own designs, create some shapes, do some basic simulations to see what the flow through it looks like. And I would strongly suggest taking a look at the tutorials. So there is a support center. There is a long list of tutorials on the website. I'll put a link to SimFlow in the description of the video, of course, as well as the starting data set if you want to play around with it. But There's plenty of tutorials in there for everything from external flow, wind through a city, airfoils, automotive. There's a basic car model that they show you how to do external flow on. And they do go through the post-processing and exporting it to Paraview. So they might give you a bit more information on some additional post-processing that you can do. Personally, I have found that the UI and the UX going through Paraview tends to be a bit cumbersome. It's tricky to get acquainted to, so I didn't want to spend a ton of time in here because I honestly don't know where everything is and how everything works. I just know some of the basics. So if you want to continue to use it, feel free. If you do like this and you want to see more with Paraview or SimFlow and you want to continue to do videos like this, then please let me know, and I'm more than happy to pursue some additional videos in this area. Maybe we can look at things like a concept car and external flow, that kind of stuff. But for right now, hopefully that gives you enough information on some basic settings and how you can interpret some of this data to better understand changes that you might make in your own designs. Now, if you have any questions on this, please let me know. If you enjoyed this series, I'd love to know that as well. I like to do these types of series, but oftentimes people don't want to sit through 4 or 5 hours of video. So it can be kind of bittersweet if we put a lot of time into something and it's just, people aren't going to use the data. But if you do like it and you want to see more of it, please let me know. Even if a handful of people enjoy this type of content, we'll keep making it. But as always, thanks for watching, and we'll see you in the next one.